Hey guys, welcome to this video where we are going to work through this blast damage challenge. I gotta say, I'm looking at this on my computer at least, like some of the formatting there is super weird and honestly super broken. It looks like maybe a kerning issue, like the things are not, like the DI are always spaced the same, but I'm gonna look into that. It might just be the font, and it might just be my computer. Because I like it, definitely all these other. It's anytime that font comes up, so I'll look into that. It's good enough for the moment. Anyway, the idea with this challenge is simply there's some code here, and initial damage divided by the distance squared. That is, the farther away you are from the impact site, the less damage you're going to take. So if you use this cannon and hit something, then something that's right at that spot is going to take the full damage. But as you move farther away, the damage goes down. And the thing about it is in this challenge, we don't want to necessarily commit to using float or int or whatever. Like we might want to preserve that and use different things. This is a great place for generic math. And so that's the intent here, is we want to make a method that uses generic math and uses this equation that's given to us. So we don't have to invent the equation, though. As long as you use generic math, if you want to tweak the equation for whatever reason, go for it. But the idea is that we're gonna make one method that's a generic method, something that none of the other challenges in the book actually ask us to do. So this will be potentially the first time you've done that, even though the book does show how to make a generic method. And then we will just use it. So let's jump over here. So the idea is what we need is a generic method. So normally, like, let's say we were doing this, and this is whenever I'm making a generic method, one of the things that is often helpful is to write it as though it's not generic. Start by saying start by just assuming that it's a specific type. So float distance. We need float initial damage and float distance. So that's usually helpful for me, because like now we can just say return initial damage divided by distance times distance. And now we can see what the method looks like with a specific type. And in fact, a lot of times that's where things start, is you start with saying, look, we're using floats in this program, so I'm going to use float. And then down the line, 6 months later, you're like, you know what? I need this code to work with doubles as well. Or I need it to work with decimals, or I need it to work with int, or whatever it is. And so you sit there saying, well, I don't want to copy and paste this code. And in fairness, like this 4 lines of code, including 2 curly braces, which actually, while we're talking about that, I could use an expression body. Poof, now it's 1 line of code. Like, to have a version of this that's that, and a version that's double. Is that so bad? No, it's not. Oh, this isn't going to work in what I just did here. Isn't compiling because these are local functions, and local functions can't have overloads. Normally, like if I threw these into a class, public class X, it'll compile just fine. So anyway, like normally I would maybe just do something like this, where I just copy it, like if I need to. That's now, especially if it's more than just this, like if I've got 50 of these methods, or if I've got, there's this, the algorithm isn't as simple as initial damage divided by distance squared. If it's something else, then I maybe don't want to just copy 50 lines of code. So that's the problem we're trying to solve here, is we can do it with just a single type really easily, but I can't just do it, with alternate types. Like I can do this here with just a single type. So if we start with that, maybe that's a pretty reasonable hint of where to start. But now we need this to be generic. We want this to work with lots of different types. So so the first thing to do obviously is let's take these things and make them a T type with a generic method. We have to put our generic type parameter right here, in the method. And now this is a generic method, and on paper, like it should work. It's very close. The catch is, this is saying I don't know what T is, and so I can't guarantee that this mysterious to be decided later T type actually supports multiplication. And actually, I think if we didn't have this, I think it would complain about the division, because it's also true there. It's just this is the first place that we run into it. So if I remove that, yeah, operator divide cannot be applied to operands of type T and T. Haha, T and T. Get it? Oh man, that was dumb. So all we need to do is include a constraint that guarantees that T has multiplication and division. And one way to do that, I think the way that I would do it here is, so generic type constraint where T is I number base T. And now I've got to add, I'm going to do Alt Enter here using system.numerics to get it to just add that for me. Bloop. So with that system.numerics, that's where this iNumberBase lives. We like most of the time, like because like system and collections.generic and system.io and like all these things are like automatically included. We don't have to do this too often, but here we do. So you got to get that using system.numerics in there for it to compile. Anyway, now with that in there, I've got iNumberBase. Access to iNumberBase, and you have to. It's just the nature of these things. iNumberBase is a generic type, and so T must be an iNumberBase of T. Kind of weird. The examples in the expansion show it. That's what you got to do, and there's reasons for it. But now this is working, and now because iNumberBase guarantees that there's a multiplication and a division operator, as well as an add and a subtract, and a couple other things as well. So now I can do this, and I can do. Oh, that was interesting. Before it was using floats when calculate damage was float. It was using floats, but just converting these values. Now this is using. The first one uses floats, and the second one uses integers. And you can see the difference. This one uses floating point arithmetic, and this one uses integer division. So I end up with 0 instead of 0.5. And I can do this with doubles and decimals. And I wonder what would happen here if I did byte. In theory, this is calling a byte version. Yep, look at that. Calculate damage with the type byte. Which it's interesting that the byte version ended up as a 1, right? And that's probably because we've just ran into limitations on the type itself. If distance, which is the second one, 20, is a, yeah, look at that. If I've ran into like an overflow issue, 20 times 20 is 400, which is bigger than the maximum value that a byte has. So it's going to wrap around and end up at a totally different value. So yeah, it's wrong. It's not the correct answer. It's close to these other ones, but it wouldn't surprise me if we just picked a different number. if we could get something wildly different. It just happens to be, there we got a 2. Divide by 0. Oh. Yeah, I should have figured that. That'll wrap around exactly at 0. Again, it shows the problem. Like this is 16 times 16 is 256, which is just barely enough to wrap around from the 255 maximum back to 0. But again, like if I had 16 in any of these, you'd see that that's not the correct answer. 16 times 16 is 256, and 200 divided by 256 is a little less than 1. So let's try a different number here. Well, now that I'm below that, now that I'm below 16, it's going to give me the right answer, because now 15 times 15 is, I don't know what off the top of my head, but less than 256. There's no wraparound, so maybe I should go bigger. Guess I'm hoping to find something that is, it might be hard to find something. I'm hoping to find something where like I end up with like a value of not anywhere near. But you know what? I can't ever end up with anything that's not, because no matter what I pick here, I'm just rambling now. In this case, that is the correct number. Anyway, the thing about it is now that I'm using bytes, it definitely could overflow, which it does. So it gives me the wrong answer because the type is so constrained. The other thing I could do here, is explicitly put the type in. And I could do that on all of these too, like if I just did. No, like you don't often need to put this in for a generic method call, but the thing is like it'll infer the type if you don't, and because I have 2 int literals here, it'll infer naturally. If I don't put this in, it'll infer, well, you must want the int version, which may not be true if I want the float version or the double or decimal version. You can see this is telling me you don't need to do this because that's what I would have inferred anyway. So anyway, generic math is a very interesting topic. The thing about every single feature in C# 11 is we ran without these features for something like 23 years. And we're, give or take, we were fine. Every feature that gets added at this point in the game are conveniences, things that make life less painful for things that happen a lot. And this is just one of those. The things that we would have done otherwise would be probably just copy it. Have either one of two things: either copy it and just have a float version and an int version and a decimal version, and it's just copy pasted code, or alternatively we just settle on one specific type and just say, look, we only need floats. Everything's going to be a float in this program, which is, both of those are reasonable strategies depending on what you're doing. This does solve a certain pain point where you really do need many and you really don't want to duplicate the code. That's the problem this solves, and most people won't really run into this. But when you have that problem, it really does hurt. So it's nice to have this generic math stuff if you need it. Oh, the other thing I was going to say is I use number base. You could use iNumber. And you could also use the specific thing. You say I multiply operators, or is it multiplication operators? It's multiply operators. And I division operator. So like you could just say like, these are like the two specific things. And at this point, I am totally gonna wrap it a little bit. And now you could actually, like, for example, if you need this to work with one of your own types, it may be easier to implement, just say, this new type that I just made, a point type or whatever, it implements I multiply operators and I division operators. And I don't want to have to implement add and subtract and like the other things that I number or I number base need. But I mean, you can already see just how much more overhead there is. So most of the time, I think like I number base or I number is all you really need. That's what I would typically do. All right. So I'm going to go back to that other approach because, like I said, I think it's just easier. And most of the time when you're dealing with generic math, it isn't that you're like, I want my own type to participate in this as well. It's usually just sometimes I need float and sometimes I need double, or sometimes I need int and sometimes I need long, or sometimes I need float, int, long, double. Like and all those scenarios work with just I number or I number base for the most part. All right. I think that's everything for this challenge. Not too bad. But I mean, generic methods are a little bit tricky. And this generic math stuff, like you end up with having to do this weirdo thing. An awesome tool when you have that problem. A lot of people won't have that problem for a long time and maybe won't ever have that problem. But it's all these C# 11 features. It's nice when you have that problem, it's nice that there's a good solution to it now. Because a lot of times the other, like the workaround, like we saw here, is it's definitely got some problems, duplicate code or whatever it is. But anyway, that is it for this challenge, and that's it for this video. So thanks for joining me, and I will see you next time.